In this video, I readdressed the problem which I had tried to solve earlier without much success, in that of defining a tailor-made hash function for a given distribution. When you know the set of keys beforehand, you have a complete list of all the keys. You are now to define a function which will pretty much preserve the order of the keys which you wish to store on the table, as well as minimize the number of collisions in the table. The size of the table is somewhat proportional, close to the size of the number of keys itself. Which is, if you take it equal, that will the chances of. But nevertheless, the objective is to minimize collisions and to use the hash function for that purpose, for that particular distribution. Now what happens inevitably if you take a particular key and the number of bits in the key there say is equal to L dash, and we assume the size of the table also some power of 2, say equal to L, we might call 2 power L dash equal to M and 2 power L equal to S. So more or less you are trying to map L dash bits to L bits in. And as always, the thinking would be to group L dash by L bits together and all that, so that as the base and all of that. But now what happens inevitably when we try to solve the problem, there are only two possibilities. When you have a key, if you choose to use the mod operator or the div, most of us use in unordered hashing, we use the mod operator because the variation in the lower order bits we know will be much significantly better than the variation in the higher order bits. Therefore, we tend to use this. But if you wish to preserve the order, the natural thinking is to use the higher order bits and to ignore the lower order bits. But the collisions there will be significantly larger. So even though, meaning the size of the bucket cannot be too small, it must be very large, and usually it will tend to grow large because the number of different quotients for which the remainder variations occur in the remainder will be far fewer than the number of remainders that occur there associated with a given quotient. So meaning for a given quotient, often the number of choices of remainders will be more than one. Quite different ideas come to mind. If the number of quotients is not many, you can always afford to keep a bitmap with the number of quotients and map for each quotient map to the table, some permutation of the table, so that the number of collisions becomes fairly small, and you can keep into account what is the actual permutation that you use there, for which part goes to when, and so on. So that's a possibility, or you could divide it into 3 parts. So keep a quotient for A, B and C. So for A you have a particular bitmap to know whether that value of A occurs. For this you can divide, say, the table LS into square root of S parts, and based on this part, say A, B and C. For B you can map a permutation of the square root of S to based on that, and then have a bitmap for that like that. So you can do that. That's a possibility, but here I'm more interested, but the purpose of making this video is to say that what is always possible is, if you associate a particular if the ratio of L dash to L, say, is equal to C, that means L bits will always be associated with L dash minus L bits, or 2 power C L dash minus. So if we take M by S is equal to D, this leading part of the quotient part here, this part is D, each value of the leading part, which is the quotient, will be associated with the different values of. So there is no way you can alter this fact. But what you can do, however, is alter the distribution of that, meaning that totally there will be s into d part values here. Right? Instead, you can associate with, ideally, since the same for different values, fewer values of quotients, different sets of remainders are chosen. Therefore, it does make sense to actually distribute d not uniformly but non-uniformly. That you can always do. One possibility, one simple possibility is, so what is possible is always sufficient. That can do it done in most cases. Therefore, let's say if we have s values here as the size of the table, then we determine values d0 and d1. d0 is for the lower part of the key and d1 for the upper part of the key, such that s by 2 times, taking only the s by 2 times d0 plus s by 2 times d1 is equal to s times d, which clearly gives us that d0 plus d1 is equal to 2 times d. What I'm doing is, for the lower order bits here, now what I'm saying is, for all those keys that are odd or that are even, all those positions that are even, and those keys which map to the even position, I'm using d0, and those which map to the odd position, I'm using d1. As the ratio for it. But if we take, instead of the lower order bit, if we choose to take the higher order bit, then it will be auto preserving. Meaning, for all those keys whose higher order bit is 1, that I've taken as s by 2 d1, and whose higher order bit, leftmost bit value is 0, it is s by 2 d0. Now, the same thing only. Now, if we move on to the next bit here, we have the value. We have taken one bit. Then we have to determine the value similarly. We have here d0, comma, d1. Then you need to determine d2, d3, d4, comma, d5. In other words, you need to determine s by 4 times d2 plus s by 4 times d3 is equal to s by 2 times d0, and s by 4 times d4 plus s by 4 times d5 is equal to s by 2 times d1. We are moving one bit to this side. So we can vary the distribution like this. So what are the different values for which roughly what are the different values for which what should d0 and d1, d2, d3, d4, d5 be. So we need to see that. That ratio. Like that we can do so for all the L bits of S. Now the choice of the values for d0, d1, d2, d3 and so on. What we can assume is, all we need is a reasonable table of, say, you can take as a reasonable value. You need not take all S values, you can take up to a small number of values, only fairly small number of values, and you can have, that should offer a fairly good, based on the table need not be completely S size S, it can be slightly smaller than that. So you can have d0 by d1 roughly equal to or number of keys that are above m by 2, less than equal to m by 2 by number of keys that are greater than or equal to. That is the number of key, let k be the key that is exactly somewhere near the mid value, n number of values that is keys here. Divide the set of key sequence of keys that you have, let k be the key which distributes the number of keys up and below exactly in middle, right? So, and this is the smallest key, which is KL is the largest key, and you are interested in the exact key that is right in the middle key. Then the ratio should be k minus ks by kl minus k should be nearly equal to d0 by d1. So before you hash, you always subtract the smallest key from it, and then use this ratio to choose between which part of S, how to divide S, right? How to divide the keys that you hash into two parts, well, d0 and d. So for all those keys which are less than k, the multiplier is d0. For all those keys which are greater than k, the multiplier is d1. But totally you do not have a uniform distribution, you will have a non-uniform distribution. This is one way by which you can afford to fill up the table so that the number of collisions is minimized. In other words, what we can do is alter the distribution. In most cases, that will prove to be sufficient. If we use a uniform distribution, does not always work out well for random selections. So we can vary the distributions and maintain a small table of values, which helps us in deciding either the hash function or the apportioning of the table as well, or both. Another possibility is to vary the distribution is as far. Now that same idea there, I have divided it into two parts. You can divide it into more than two parts also. So if in general, if you will divide it into, say, C parts, then you will need d0 plus d1 plus d2 and so on up to dc minus 1, or sorry, c minus 1 must be equal to c times d. The same thing will only appear now. So apart from this, there is also another way in which we may go about trying to apportion or distribute. The keys this way. In this one, another alternative is, so we have the set of values of the keys, say 0, 1, 2, 3, 4 and so on. We divide the keys into two parts, even and odd. There, for this one, here the increment in the key is only 1, but we assume some other value for the increment which is much larger. For this one, 0, 2, 4 and so on, the increment we assume, or the difference we assume is say D0. For this one, 1, 3, 5, 7 and all that, we assume D1. So clearly D0 must be greater than D1. Okay. Let D1 equal to D0 minus C0. But we require also that D1 okay. Now we need to add plus D1 equal to 2D1 must be greater than D0, or D1 must be D1, that is D0 minus C, 2 times D0 minus C must be greater than D0, or D0 is greater than 2C, or C is less than D0 by 2. Sorry, not C, D0 minus C0. Yeah. C0 less than D0 by 2. If we divide it only into two alternate or even. Now what we can do is we can take another, it's similar to your modular arithmetic only. Now instead of dividing it into two, having two different values, D0 and D1 for odd and even keys, multipliers, we can assume some other, for 3 also we can do the same thing. Then what will happen is, the same thing only, we will have here 0, 1, 2, 3, 4, 5. If we have here, then you will have these values. For 0 and 3, if we take D0, then for 1, 4 and so on, if we take D1, and if we 2, 5 and all that, if we take D2, we require D0 greater than D1 greater than D2, and D1 we have D1 equal to D0 minus C0, D2 equal to D1 minus C1. Now we require this is equal to D0 minus 2 times minus C0 plus minus C0 plus C1. Okay, now we require 2D2 must be greater than D0, that is we require 2 times D2 greater than D0, 2 times D0 minus C0 plus C1 greater than D0. In other words, D0 greater than 2 times C0 plus C1. In other words, we require C0 plus C1 by 2 times C0 plus C1 less than D0 by 2. You can keep extending it to more and more. What you will find is the only condition is all of these must be greater, but sum of all Ci must be greater than, less than, always less than D0 by 2. So you can take this value to be floor of D0 plus D0 mod 2 by 2 minus 1 as this value. So you can divide it into so many parts. Now based on a given set of keys, if those keys are probably known, you can have a table of values for C0, C1 up to C, and any number of reasonable values, C0, C1, C2 and so on, so that the number of values a reasonable size table, so that will help you to decide where the number of collisions is minimal.